Hello everybody, we have started discussing on Kalman filter for last couple of lectures. We actually given some overview and then followed up with some basic concepts of random variables followed by Kalman filter derivation in continuous time linear time invariant system, that platform actually. So, we will develop further and our motivation is to go towards external Kalman filter and if possible uncentered Kalman filter as well. That is what people use these days very heavily, and that is what we develop towards that. So, this particular lecture will again have a very quick overview of what we discussed in the last class, followed by will the discrete time domain derivation actually, and then we will continue further on those lines actually. Ultimately, the idea will be to merge discrete time and continuous time together. Alright, so let us get started. A very quick overview of Kalman filter design for linear time invariant system and as again continuous time domain of whatever we have discussed in the last lecture. The system dynamics was something, we consider here is something like this: x dot is x plus v plus z w, y is c x plus v, w and v are continuous time process and sensor noises respectively. I also had some assumptions. The initial conditions are described as something like a mean value and associated covariance matrix, and followed by all these assumptions that W and V are uncorrelated white noise, and then they are also mutually orthogonal. All these x naught W and V are mutually orthogonal, things like that. And using this relationship somewhere down the line, we are able to derive this continuous time Kalman filter. So, how did we do that? Something like this. The objective was to estimate this x hat of t using the system dynamics as well as a sequence of measurements as accurately as possible. That was our aim. That means, the error of estimation x minus x hat t should become very small, or ideally it should go to 0 as t tends to infinity. So, that was our objective actually. So, how did we do that? We had a estimator dynamics which we took it in this form: x hat dot is a x hat plus v u plus k e times y minus y hat, and where x hat was defined as expected value of x and then y hat it turns out that it is nothing but c x hat, because E v is 0, expected value of E is 0. So, the whole point is how do we design this Kalman gain k e, but then we had some derivations like this. So, first we told we will define something like a process this P of t, which is nothing but the error covariance matrix. So, this was defined like that, and we wanted to study a dynamics of that, how it evolves, where it goes and things like that actually. So, we had this P dot derivation, which is nothing but expected value of all that, because expected value and derivatives are both linear operators, they commute. So, the derivative goes inside and it follows like this, and it turns out that this P dot can be expressed as something like this plus this entire same thing whole transpose. So, then we thought what is this quantity. Okay. So, that quantity is for knowing that we know this there is a term called x tilde dot. So, for knowing x tilde dot we have to go back to the x tilde definition, and then from this definition this x tilde dot comes out naturally. So, you have x tilde dot is x dot minus x hat dot, which is the put back the dynamics, okay, and x hat dot is the observer dynamics. So, put it back and then try to simplify further. It turns out that this is something that what we define is a minus k e c is a naught x tilde plus these additional quantities g w minus k e v. Yeah. So, obviously, the error dynamics gets affected by both process noise as well as sensor noise basically. Then this term is ready now, but what our aim was not that. Our aim is to get some value something like this. So, then we told what is this one? This one we expected value of that, and then we try to expand the algebra inside and then invoke this idea that expected value is a linear operator. So, we can separate it out, and then it turns out that this quantity by definition is nothing but p. Okay. However, these quantities we need to still evaluate. Okay. Expected value of this in this case we still need to evaluate actually. So, where are you heading to? These quantities, okay, For knowing this, we need to have a solution of x tilde actually. Okay, what we have got so far is x tilde dot. So, we need to get a solution for that, but then you can think that okay, this x tilde dot equation what you have here is something like a homogeneous part and a time varying input. Okay. So, if this is like that, we know the solution, and the solution is coming from linear time invariant systems theory directly. Well, okay, this solution can be represented something like an exponential term with a initial condition plus this integral term, this convolution integral sort of thing, where 0 to t e to the power n r t minus tau, all this actually. This is nothing but the entire thing is nothing but a time varying input actually. Okay. So, then again linear integration is a linear operator. So, we can separate it out and then we can evaluate, because I mean this is the solution of x tilde t, but this is what is our aim? Our aim is to evaluate this quantities actually. So, we go back and substitute the term for that quantity, okay, r of w x tilde. So, this is nothing but by definition is nothing but expected value of w and x tilde transpose. Now, we have got a expression for x tilde thing. So, we put it back there, okay. And it turns out that because of mutual orthogonality relationships and all, everything else will go, v and x tilde dot will go with as long as it is multiplied with w actually. So, only term that will remain is w term itself, and again you can excite this linear operator concept, and it puts this w inside. And then here it turns out that the w times w transpose appears, okay, and this again this expected value will go inside the integral, and the expected value of this thing, okay, by definition we started I mean this definition, that expected value of w transpose is nothing but q. Okay. So, because of that it turns out that this is nothing but a delta operator will come in here, and we also, I mean there was a small tethering there last time, but anyway this turns out that if you have a delta operator sitting here, something like integral a to b f of t and multiplied by a delta operator which is well, let us say t minus tau, okay, dt sort of thing, or t minus let us say c, okay, sorry. All right, let us say t minus c into dt. Okay, this turns out that okay, if it is if c lies completely inside the interval of a and b, then it is nothing but f of c, and if it is somewhere either a or b, then it is something like half of f of a or half of f of b. Okay. So, this is this one is provided t is completely inside a b. This is if sorry, if c, sorry, one second, if c is completely inside a b, and if this one is if c is equal to a. Okay, what happened there? Okay. Okay, so this is actually c is equal to a, and this one if c is equal to b. Okay, so that means as long as c is completely inside the interval of this integral, so that takes the form of just I mean f of c, but if it is somewhere on the boundary, then half term will come into picture. Because of that, I mean this interval, what this integral what you see, there is a half term here, okay, but tau is getting evaluated at t, because t happens to be one of the, I mean limits of the integral. So, then okay, this is nothing but I mean now it is e to the power 0, because t equal to tau, then e to the power 0 is nothing but identity, and hence you get something like this. So, we got now a kind of a deterministic quantity for this term, cross covariance matrix sort of thing. And then for this quantity, we can exactly follow the similar line, but instead of this, I mean only retaining this, now it will be only this quantity with a negative sign, of course. So, this algebra follows exactly similar to that. Again you will have a delta function there, and it turns out that something like minus r into k transpose. So, then we told okay, now we are ready now to put everything into place. So, our motivation was to evaluate this first. So, this term was already there. Now, about these two terms, we got something like R W x tilde is something like this and R V x tilde is something like this. So, now this expression turns out to be something like that. So, going back, tell okay, our P dot was something like this term plus the same term transpose. So, hence P dot is nothing but same term plus same term transpose, I mean this term plus this exact same term transpose. So, you do the algebra right, and then combine these terms, it turns out to be something like that. Now, here is a problem where it tell okay, we still need to design Ke, but we need a solution for P also for that actually. Okay. So, here we have to go back and excite a theorem sort of thing. It tells okay, on steady state this P dot is going to go to 0 provided this quantity A naught, which is A minus K is stable actually. Okay. So, and we are what you are interested in is a positive semi definite solution for P of t. So, this is this turns out to be like this. Okay. So, essentially what it means is because P of t is something by I mean P of t is something like this, what it also means is the smaller the P, the better actually, better the estimate. So, essentially what I am telling here is we want to minimize P subject to this constraint equation. So, we have to formulate some sort of optimization problem where we want to minimize J is half of that subject to this constraint. Okay. But this is a matrix equation constraint, okay, and this is a matrix norm. Stress is also kind of a norm actually. All right. So, then what he told is okay, the formulation as the solution turns out to be something like that. You formulate an augmented cost function and then take all these partial derivatives with respect to P, Ke as well as this Lagrange multiplier matrix S basically. So, all these three constraints equation needs to be satisfied together, and hence if you solve it one by one, it turns out that Ke is nothing but P C transpose R inverse actually. So, that you got an expression for Ke. Now, how about P? P can be obtained as a solution of this, okay, because all the what you are doing here is getting this three equations satisfied together basically. So, it turns out that this equation must be satisfied, okay, after putting all this expression for Ke, and hence it I mean this is nothing but what is called as filter Rickard equation actually. So, essentially we need to solve this equation and then evaluate this Kalman gain like this and then put it back in the observer equation that we know actually. So, that was the whole development in the framework of continuous time LTI. Okay, but it turns out that certain I mean invariably we have assumed one small thing here which has a big implication that the measurement equations we also assumed they are continuous time, and unfortunately the continuous time measurements are typically not feasible. So, next people thought okay, how about going into discrete time actually, because if you have a continuous time system dynamic equation, you can always discretize it in using some discretized numerical equation, I mean numerical integration formula and things like that. So, that will give us a platform for discrete time system dynamics, whereas the discrete time sensor measurements are still available with us actually directly. So, that makes it the platform some sort of a compatible actually. So, then that is the whole idea that wanted to see Kalman filter design for linear time, I mean it is a discrete time thing, but before that okay, there is one more assumption that we I mean we had it here in the entire beginning. If I go back, we also told that this is nothing but the linear time invariant system. That means A, B and I mean C, all that what you see, these are all not varying with time actually. Now, what if they are time varying things actually? Okay. So, that is natural generalization before you go to discrete time domain. Alright. So, then let us see that okay, this development is very parallel to what we had done for I mean continuous time LTI system. So, let us see what is the derivation for that. So, the problem definition is almost same what we have seen before. The only difference is all the system dynamic matrices A, B, G, C and all that, they are all now time varying matrices. Okay, so they take different values at different point of time actually. So, then now what actually? Alright, so the objective remains exactly same again. We want to have some sort of an estimate for which the error should go to 0 as t goes to infinity. So, we again had the same filter dynamics, okay, and then we have this error definition x tilde something like this, Then we have this error dynamics, we exactly derive similar way. The only thing that we need to keep in mind is that all the matrices that we are talking now is time varying. Okay. So, then it will end up with the same error dynamics, but the difference here is, okay, this term is actually time varying. Okay. So, we cannot excite the solution in the form of exponential actually. Okay. However, we know that even if there is a time varying system dynamics, but still it is linear system, then we can have solutions of this form where phi comes into picture, okay, and this phi turns out to be something like state transition matrix. Okay. So, using this state transition matrix concept, we can still write the solution, okay, something like this, okay, and then we go back to the error covariance matrix definition. P of t is nothing but that. Okay. So, exactly is proceeding the very similar manner, and that is one of the reasons why I wanted to review that last lecture material. So, we again go back to the definition of what is P, and then P dot is nothing but expected value of derivative all that, this derivative times that plus this times that derivative, all sort of things. You can derive everything, and then turns out to be something like this. Okay. Okay. Now, what you can say is we cannot excite the thing that on steady state things will go to 0, that is not possible. Okay, because it is all happening in a time varying sense. Okay, it depends again the way this matrices vary and things like that. So, we cannot excite this condition of asymptotic stability and things like that. When t goes to infinity, we cannot claim that P of t should go to 0, that may not happen here. So, if that does not happen, then the next best thing that probably comes to mind is how can we do something, so that the rate of change will be minimum actually. That means, P dot will turn out to be minimum. Okay. So, then we want to minimize P dot, and hence we see what is this trace of P dot actually. Okay. So, trace it turns out to be something like this. Okay. And since trace of this quantity is also trace of the same quantity transpose, or same quantity transpose turns out to be something like this. Okay. The transpose will take a reverse sequence. So, it will be K transpose whole transpose is again K, C transpose whole transpose is C, and then P transpose coming here. And remember, P is a symmetric matrix. So, P transpose is P. So, that turns out to be like this actually. So, this fact has been utilized somewhere here actually. Now, the problem turns out to be like we do not want to minimize P per se, but we want to minimize P dot. So, minimize this quantity. Okay. J is half of trace of P dot actually. Okay. And minimize with respect to what? We minimize with respect to K basically. Okay. So, then the necessary condition is del J by del K has to be equal to 0, and del J by del K, if you do this operator, then it turns out that P dot is this expression, okay, because these two quantities, I mean P dot, okay, trace of P dot is this quantity. Okay. And trace of P dot happens to be, I mean this P dot happens to be this minus that. If you substitute back your this expression, okay, sorry, this trace of P dot, if you simplify the algebra and things like that, it will turn out to be something like this quantity basically. Okay. So, this quantity, if I have this derivative with respect to K E, then I can take it inside. Tell okay, this expression is nothing but this expression now, and this expression if it has to be equal to 0, that means if I solve for K E takes the form of, okay, so I mean this, remember K E times R is equal to P times C transpose. So, R is in the right hand side, so you have to take right hand side inverse only, we do not have a choice of left side. So, K E turns out to be something like P C transpose R inverse again, exactly the same expression what you have seen before, but all these are time varying now basically. Okay. Now, that P dot, what you are talking, okay, there is a P term where P comes from the solution of this P dot equation, okay, with initial condition that we know basically. P dot is nothing but P of 0 is nothing but expected value of this quantity. Well, this is actually available with us in some guess form and all that. But anyway, so that is I mean P naught is available. So, P dot is available. So, that utilizing that we should be able to get a solution for P of t actually. Okay. So, that is the approach. The expression remains same, but P cannot talk about a steady state Riccati equation solution, but it should be a solution of this differential equation with this initial condition actually. Now, what happens to the time invariant steady state case? That is a special case sort of thing. There if it is time invariant, P dot has to go to 0, and if P dot has to go to 0, this expression remains same, but this expression turns out to be nothing but the same algebraic Riccati equation for filter design. Okay. So, essentially what it means, the solution is same as what you have derived before actually. Okay. So, the only difference is the Riccati equation needs to be solved from this initial condition and this differential equation. That's the bottom line actually. So, summary sense, we have to have we should initialize this state x at 0, and then we should propagate P of t from filter Riccati equation with this initial condition, compute the Kalman gain, and then propagate this filter dynamics. Okay. So, that is as simple as that actually. Alright, so everything good, but there are other practical difficulties and things like that, which I encourage all of you to read some textbooks and all that, for mainly coming from numerical things, as well as the difficulty of for guessing some good initial conditions and things like that. But as long as it is linear system dynamics and all, it should not be too much of a concern. Eventually, everything will converge actually. That is not a problem at all. Okay. Alright, we will continue further. And then tell, okay, what about this filter stability issue basically, because everything is changing in time, I do not know what will happen and things like that. So, then we will define this xc tilde for algebra simplicity. We introduce this new notation, xc tilde is expected value of x tilde, and then xc tilde is this expected value of x tilde dot, and we have derived this before, that this dy dt of this quantity turns out to be something like this actually. Okay. So, this is available with us, and this expression we know basically. Okay. So, then we tell, okay, we will select a Lyapunov function, okay, which is nothing but this kind of this form, and again remember Lyapunov function can be chosen anything as long as they satisfy certain properties like positive definiteness and all that. So, this is a positive definite function, because P is positive definite, P inverse is also positive definite. So, we can select it that way. Okay. So, what we also know that in the derivatives, so the Lyapunov theory will tell you analyze, select a positive definite V, and then with respect to that selection, V dot has to be negative definite, something like that. So, when you take V dot, remember P inverse is also time varying quantity, that means we will also need a derivative for P inverse actually, dy dt of P inverse. Okay. So, that is why it will, okay, the exciting this quantity P times P inverse is identity, we take derivative of both sides, okay, and this derivative, because identity is constant matrix, this turns out to be 0. So, when you solve for this, then if you solve for this quantity, then it turns out that this is the expression actually for P dot inverse. So, we go back to V and then tell what is V dot now. So, V dot turns out to be all these three expressions, first term, the rest of the terms, xc dot transpose, then this quantity, then this two quantity times xc dot, and then middle quantity dot actually, P inverse dot. Now, P inverse dot is available. So, this is our P inverse dot, and this xc tilde dot is available, that is what it is. And xc tilde dot transpose is transpose of the entire thing, which is a reverse transpose sort of thing. So, we see xc tilde transpose coming first and other things coming later actually. So, we put it back here, okay, and now we can expand this brackets and then excite this fact that K is nothing but P C transpose R inverse actually. And also we know that that P dot is in this form. So, if you expand all that, put this P dot expression, expand and do this necessary algebra, it will turn out that V dot is nothing but this expression actually. Okay. So, clearly if Q is positive semi definite and R is positive definite, okay, remember Q is positive semi definite at least here. So, this quantity, this is a symmetric term again, and P is again positive definite term. Okay. So, this term remains positive semi definite, whereas this term, because R is positive definite, R inverse is also positive definite, and this is also a symmetric term, C transpose C sort of thing. So, this turns out to be positive definite actually. Okay. So, this means if this selection is met, Q is positive semi definite and R is positive definite, then V dot is guaranteed to be negative definite. Okay. So, stability condition is met, but this is local asymptotic stability. But it also turns out that the way we selected V is also radially unbounded actually. Okay. And it also is shown that it is not, it is actually a decrescent function basically. Okay. These are all concepts from nonlinear control theory basically. Those of you are interested can see some books on that, or you can see my other course where we talked a little bit on on Lyapunov theory. There are some couple of lectures there, and you can see some of those lectures to see some of these concepts actually. Okay. So, the condition turns out that if V dot is negative definite, and on top of that if V is radially unbounded and it is also decrescent, then it is actually it satisfies this global stability behavior, and hence we can claim that this particular x tilde t, that dynamics is globally uniformly asymptotically stable basically. Okay. So, this is a very strong notation sort of thing, strong result basically. Okay. So, it is asymptotically stable and it is uniformly asymptotically stable. That means, it does not matter when you start, geometry of T naught actually, and it is also this result is globally true. So, that is what we are telling, globally uniformly asymptotically stable. Alright. So, this gives us a kind of lot of confidence that nothing will go bad if you implement this way. Even if you start with some arbitrary P naught, it may take a little more time to converge, but eventually it will converge actually. Okay, nothing will go bad really. So, that is a generalization of Kalman filter in continuous time from linear time invariant systems to time varying system. Okay. But as I was talking some time back, real time back, what we are interested is a framework where we can actually incorporate a discrete measurement equation actually. So, that leads to this concept of discrete time Kalman filter. In other words, the system dynamics can be continuous, and it is not typically continuous, but we can mathematically discretize it, whereas sensor outputs are typically discrete and we can't make it continuous. I mean the tape, it may not be feasible because the sampling rate may not be sufficiently fast to interpret it that way actually. So, let us go and see how we can derive everything in the form of discrete time. And here it does not make sense to talk too much on time invariant or time varying and things like that, both will converge to the same thing. So, in general we talk about time varying linear systems and discrete time domain. So, we have this system dynamics where xk plus 1 is given something like this and yk is something like this. Okay. K stands for time step actually. Okay. And here this wk and vk are again assumed to be 0 mean, white uncorrelated, Gaussian and white noise actually. Okay. So, what you are telling here is again this similar concept, but in the form of Kronecker delta this time. Okay. And this direct delta and Kronecker delta have kind of similar properties, but they are I mean this operates on the discrete domain, the other one operates in the continuous domain actually. So, the Kronecker delta Kj is defined as something like this. If k is not equal to j, it is 0. It is k is equal to j, it is 1 actually. Okay. So, when you take expected value of wk times wj transpose, there is some value, okay, which is the qk provided j is equal to k, otherwise it is 0. Similarly, expected value of ek times vj transpose is rk provided j is equal to k, otherwise it is 0 basically. And because of orthogonality and things like that, they are uncorrelated and things. So, that means expected value of ek times wk transpose, it turns out to be 0 basically. So, there are two ways of looking at it, and the first way is very popular and logically so. One thing, I mean this form tells, okay, I will propose it this way. That means, there is a predictor equation and there is a corrector equation. Okay. And if you can substitute this equation 2 in 1, you can always get this form, which looks very close to what you have done in continuous time actually. Okay. alright. So, this is actually observer form or recursive form they call, okay. And but this form turns out to be much more intuitive and easy to implement, and logically it makes a lot of sense also basically. Here you see, okay, what is the difference here? Here you see all minus here, minus here, minus here, and here you see some superscript being minus sometime plus sometimes like that, and the implication is also, I mean, there, okay. Okay. Okay, let me go to that implication first and come back to here actually probably. So, this is discrete time form. So, the implication I was talking about implication of this. So, what it turns out, this prediction, you think about something like starting at some sort of a plus value and going to this minus value using this prediction sort of thing, and starting with a minus value you go to the corrected value plus value using this measurement equation. With this, remember yk is a measurement value basically. So, what it means is something like, okay, I have this pictorial representation of something like this. If you see this time domain, okay, which is some k starts from, okay, this is k, this is k plus 1, let us say, this is k plus 2. So, something like this, and what happens is I have some value, okay, I will predict, okay. So, let us say this is x k plus, I will predict, and I will end up with x k plus 1 minus. Then I update this, and then once I update, this value will change to some other value, and that value I will call as x k plus 1 plus. Then I will predict again, and then I will end up with something like x k plus 2 minus, and here again there is a measurement. Measurement can be either way, positive or negative, does not matter. Finally, I will get x k plus 2 plus. Okay. So, this way it will continue. So, in other words, there is prediction, okay. I know some value, there is prediction, correction, prediction, correction, like that actually. Okay. Alright. So, starting with the updated value, I can go for a predicted value, then update it again and things like that. That is why it is very logical actually, and it also makes it convenient for computer programming as well. Alright. So, that is this what is written here. Prediction correction form is more popular, and it is logical, more structured, and easy to implement as well. Okay. It also leads to the logical extension into this EK for extended Kalman filter. When you see it, actually this is the form that is most widely used, and that is in EKF domain actually, prediction and then correction. Okay. And also it gives us a platform. So, okay, just if you see this form, it gives us a platform that during prediction we do not really have to use this discretized equation. We can use another discretized equation if we really want to, with higher accuracy actually. Okay. Even though the theory assumes that, okay, we do it one step all the thing, we can in the prediction stage someone can think about implementing in the some sort of higher order numerical integration scheme. That also gives a platform to implement that way. Anyway, so this is what it is. So, now the question is how do we make sure that estimation is correct or estimation is good actually. In other words, error of estimation is small. That is what our objective all the time. So, when you talk about error, now error is in force domain. So, first of all you had something like, okay, if you see this picture as well, there was some value, okay, from which it was updated. Okay. So, this is x k minus basically. Alright. So, this is I mean, if you see this picture, turns out that, okay, k, if I talk about time step t k or k, I have a value for x k minus and x k plus. Similarly, at k plus 1, I have a value for x k plus 1 minus and x k plus 1 plus. So, essentially, if I look at this k and k plus 1, I essentially observe that there can be 4 errors actually. Error can come in here, error can come in there, error can come in here, or error can come in there. So, then I have to define 4 error quantities, okay, and first error quantity is x k tilde minus, which is x k minus x hat x k hat minus, and similarly x tilde k plus, which is x k minus x k hat plus. Similarly, you can define that at time step k plus 1. Okay. Now, you define what is this error covariance matrix. and this error covariance matrix turns out to be something depending on these quantities, we have to define the corresponding quantities. That means, if I start with this quantity, then error covariance matrix Pk minus turns out to be expected value of this quantity, whatever I have here, xk tilde minus transpose, same quantity. Similarly, with this, if I tell Pk plus, then I have to take this quantity times this same quantity transpose, that is what is written here. Similarly, things are here. And do not get confused too much with the math, is all about good bookkeeping actually. So, essentially what you are telling is we want to derive these expressions, and finally select this Kalman gain in such a way. Remember, it comes here in the correction equation actually. I want to derive this Kek in such a way that ultimately when I update, my Pk plus will turn out to be minimum. That is the whole idea there actually. Because when I update, I want to see a good update value. Updated value should be very good. That means, this quantity, this Pk plus has to be minimum actually. And similarly, Pk1 plus also needs to be minimum, things like that actually. Alright, to have these quantities, different quantities, we need to analyze this quantity first, because this is coming here, and this one is related to each of the term here is related to the system dynamics. So, we analyze this quantity, error is nothing but true value minus the estimated value at k plus 1. So, true value is system dynamics, it comes from something like this, estimated value is something like this from the from the predictor corrector equation. This quantity is available, put it back here. So, once you put it back, this k can be common. So, you have this xk minus xk hat plus nothing but xk tilde plus this quantity, and then buk and buk will get cancelled out. This quantity gets cancelled out actually. So, we combine this first term with first term and leave the other one actually. Then gk wk will turn out to be like this. So, this expression is available now. So, what about this? Because this expression is now available. So, we can always talk about this quantity, which is expected value of this quantity times the same quantity transpose. So, now we have got an expression for that quantity plus the same quantity transpose. So, what we do now is expand this transpose and then multiply this this matrix, these two matrices. So, we get 4 terms actually. So, if you do this algebra carefully, it will end up with something like this, and again excite this fact that expected value is a linear operator. So, we can separate it out all the things, but here we can observe that there is a multiplication of wk and xk tilde plus. Similarly, is xk tilde plus and wk again. So, that means these are not correlated. So, essentially these two quantities will go to 0. So, we are left out with this one and that one. This one turns out to be nothing but this by definition, and this one what we have here is nothing but qk again by definition actually. So, essentially this pk plus 1 minus which is essentially an estimate of how much the error it is after prediction turns out to be like this. And we have to obviously start with this, because this is, remember, this is kind of a propagation equation. So, we need some sort of p naught minus value, and it comes from there actually. Now, expression for pk plus, then what is pk plus? Essentially expected value of this times that same quantity transpose. So, we have to have some idea about this quantity. So, this is again by definition, you go back to the definition and put here something like this, xk is xk, we return it like that, but xk plus is this quantity. We have this xk plus is update quantity or corrector equation, put it back there. Now, we expand all this, xk plus, and now yk is nothing but ck xk plus vk. So, we put it yk expression here and then expand all that, and it turns out that we can write it in this form actually. okay, because now here is xk, here is xk hat. So, when you talk about this quantity, this is nothing but that by definition, the error between these two. Okay. So, error after update is a function of error before update, which is very logical actually, and then this Vk quantity also. Okay. So, alright, so this is the type of thing. So, that means once you have I mean what you have now is xk tilde plus, which is something like this. So, what is our aim? Our aim is to analyze this quantity pk plus, which is given as something like xk plus times xk tilde plus transpose. So, this quantity is something like this, that is what we derived now, and hence we put it back here, this quantity plus the same quantity transpose again, and we carry out the standard algebra, okay, and see. I mean again I suggest that you take a sheet of pen and paper and try to derive it yourself, then only you can see what is going on here very clearly. Then ultimately it turns out that okay, we have this this Vk x tilde and things like that is not there. So, that will go to 0. So, we will end up with this quantity, which is similar quantity. So, that is nothing but Pk minus. So, this term will be retained, this will go to 0, this will go to 0, and this term will be retained in the form of this. Okay. So, we got an expression for error covariance matrix update actually. So, now what is our aim? Aim is to have this quantity as small as possible. Okay. So, after update at a particular time instant, I want that estimation to be good. That means, the error between estimated value and true value should be as small as possible, and this is a indicator of that. So, that means, whatever pk plus expression is there, I want to minimize that actually. Okay. So, essentially the problem is like this, we want to select a kek in such a manner that trace of this pk plus is minimized. In other words, minimize j is a performance index, half of trace of pk plus with a proper selection of kek. So, obviously, we have to excite this necessary condition that del j by del kek equal to 0. So, that del j by del kek, if you just see this expression turns out to be like this, because j is nothing but trace of pk plus and pk plus is available here. Okay. So, using standard matrix algebra calculus, calculus for matrix expressions, we can derive something like this. This del j by del kek turns out to be like this, and here is actually a linear equation in terms of k, and fortunately k happens to be in the left hand side in both the expressions. So, it is easy to solve. So, you take kek in the left hand side, take this, and then that this pk minus times ck transpose, which happens with a minus sign, goes to the right hand side, appears here, and then kek is ultimately something like, remember this is a right side product. So, we have to multiply with right side inverse actually. Essentially what it means is kek is pk minus times ck transpose, which is this quantity, plus this matrix inverse actually. Okay. So, what you are having here? We got an expression for pkek. Alright. Now, pk minus pk plus, we got an expression for that also. Okay. Now, pk, because remember we need a expression for update of this covariance matrix as well. So, we got that, and then we got an expression for Kalman gain also basically. So, we are all kind of done. There is a small interesting observation here, that if we use this expression again and revisit this expression, okay, then we can actually get it a little bit simplified expression, okay, because we put it back, whatever we know here, if we put it back, then sorry, not that. Okay, what I mean is, you start with this expression, okay, and try to simplify this. Okay, this transpose goes inside, and then try to kind of expand this bracket and things like that. It turns out that these two quantities cancel out. Okay, these two quantities will get cancelled out, and we left out with that. So, it turns out to be a much simplified expression, but unfortunately, it is not a very good idea to implement this, because it will have numerical problems actually. This is not a symmetric expression. So, in other words, there is a chance that the symmetricity will be lost because of some other problems like round of errors and all that actually. So, there is a strong recommendation in the literature and books that even though this simplification is possible, never get tempted towards using this. You still use this equation only. Alright. So, what is the summary here? After all this, we have this state equation, okay, in the form of discrete time, but discrete time varying system, and measurement equation is given something like this with the usual assumptions that this W and V are white noise, uncorrelated and things like that. We have got we have to initialize the filter and we initialize that way, okay, with values for x hat naught minus and p naught minus. Okay. Then we compute this, okay, which is all function of minus, remember that k e k happens to be a function of all minus k values. Okay. So, evaluate that, but soon we have to update it actually, okay, but using this k e k we update this state equation in this form, and here is that measurement will come and help us actually. So, this is the Kalman gain computation part. Then we will use that for update, and we update both. We update the state equation, I mean state values, and update the noise the covariance matrix also, basically error covariance matrix. So, this is initialization, this is gain computation at every step, and then this is update equation. We update the states like this, and we update the covariance matrix also like this, and again this expression is preferable, this is not preferable. Okay. Then we have this propagation after that. Okay. The propagation turns out to be like this. This is system dynamics. We can propagate directly, and remember there is no noise which is taken into account. While propagating, you can't have a noise. The noise is something that is unknown actually. So, we just propagate with the known part of the system dynamics, okay. And then we propagate this P matrix also, and Pk minus 1 plus Pk plus 1 minus has been derived also basically, okay. This one. Using this expression we can propagate the Pk plus we can get an expression for Pk plus 1 minus actually, okay. So, this is update, then you propagate, then again you go back to Kalman gain, you compute that quickly and then update and then propagate like that actually, okay. So, that will continue that way. So, this is all about discrete time equation implementation of Kalman filter, but some people can also think okay, we want to implement in a direct way. In other words, we can also go back and implement the direct recursive waveform actually, and there is no point in having minus plus and all that there, because everything happens at the same time sort of thing. So, minus plus superscript notation is dropped here, and you can go back and tell okay, this is my this observer equation where I need a k e k. So, k e k I will compute it that way, where p k we need a p k, but p k will turn out to be from this propagation we will obtain p k. We initialize p k, but using this equation we can propagate p k actually, okay. So, this is a different alternate form, but I mean to my knowledge and many people will also prefer the prediction correction form actually. It is very intuitive and easy for programming, things like that actually. Alright. So, this particular lecture is good enough for understanding this. What we discussed here is continuous time in linear system, and revisited all that, and then using those derivation ideas we had derived this same things for time varying linear system as well. Then we went to this the discrete time form, and then we had this derivation of all these equations, where we have an idea of how to implement it both in predictor and correction form as well as this direct form actually. Alright, so for the next class onwards, we will go back to the real problem of nonlinear systems and try to see what way we can extend these ideas for this external Kalman filter and beyond actually, which is what is used in practice actually. Alright, so this much in this class. Thank you.